So we're now going to start talking about a very interesting framework for doing parallel programming with concurrent Java. And this is something that's called the fork join framework. And so what we're going to do in this part of the lesson is discuss how the Java fork join framework can be used to process tasks in parallel. As we'll see numerous times throughout this discussion, the Java fork join pool provides a so-called high performance, fine-grained task execution framework for data parallelism. And we'll talk in a minute about what data parallelism is, but that's essentially a nice, pithy definition of what the fork join framework is all about. It also provides a parallel computing engine that's used by other higher level frameworks that are part of modern Java. For example, Java Parallel Streams uses the common fork join pool, which we'll talk about later, as its parallel execution engine. Java Completable Futures, which is another interesting framework, uses the fork join pool for its processing by default, although you can override various methods and executors when you create a Java Completable Future to have it use other computing engines. But by default, it also uses the common fork join pool. So this obviously must be an important class or framework if it's used throughout these other parallel computing engines. What it does is it provides a style of parallel programming that solves problems by something known as divide and conquer, very common paradigm for dealing with large problems. You've undoubtedly learned about the divide and conquer model if you've studied things like quicksort or heap sort or merge sort, where you take a large problem and you break it up into smaller chunks, and then you solve those chunks. And now in this particular case, you're going to solve those chunks in parallel, but you can also just solve them sequentially by breaking a big problem up into a small problem. And so the way the general divide and conquer algorithm works is you need to solve the entire problem. And if the problem is small enough, then you simply solve it directly using some sequential algorithm. And if the problem is bigger than the small enough part, then you split the problem up into independent chunks or parts. In this case, you will fork new subtasks to solve each of the parts. You then have those run in parallel. They get joined back together as they complete, and then you compose a result, a composite result typically, from the results of the subresults. And so that's basically the way things work. And we'll learn about this as we go through, and you'll get a chance to program the fork join framework in programming assignment 4A. So this is basically how the process works in a bit more detail. So you take the original source of the data and you split it up into a bunch of so-called subtasks. And as we'll see, that typically works by dividing things up into chunks or little small pieces. And the way that this is done in the fork join framework is by forking. And that's why it's the fork join framework, because we're going to fork the big pieces into smaller chunks. And typically the way this works is that tasks or subtasks will split itself up into smaller and smaller pieces until the work becomes too insignificant to split further. So at some point you will stop splitting or stop forking, and then you'll just go ahead and directly solve those problems. And so what happens is once you split everything up into atomic sized chunks, then those atomic sized chunks will all run in parallel, but each chunk will be processed sequentially. So another way of looking at this is that each chunk is then allocated to a thread that runs in a pool of threads that's mapped to the underlying processor cores. And each chunk runs sequentially, but all the chunks together run in parallel. And this diagram kind of shows how that would work. Typically, the execution of the chunks in parallel is performed by the Java fork join framework in conjunction with the Java execution environment, the Java virtual machine, for example, or the Android runtime, the underlying operating system, the operating system kernel, and of course, deep at the bowels of the whole thing will be the underlying hardware cores, which are actually doing the actual processing. So there's a number of different layers involved. And if you recall our previous discussion from last week about Java threads, you know what's involved now with Java threads. So there's a bunch of different layers there taking place as well. The subtasks, of course, will run in parallel on different hardware cores. And as we'll see as we go through this, by default, typically the number of cores that are used in the Java fork join framework is going to correspond to the number of threads that are part of the pool size. So give or take, and we'll talk more about the details later, there's roughly as many threads in a fork join pool as there are cores on the machine. And we'll get into the nuances of this as we go a little further along. As you might expect, if you have split your program up into smaller chunks, and those chunks can run independently in a so-called embarrassingly parallel model, then performance will typically go up probably close to linearly, in fact, as the number of cores increases. So if you have 4 cores, it'll run at 4x roughly more than 1 core. If you have 8 cores, it'll run at roughly 8x. And if you have 16 cores, it'll run at roughly 16x. And obviously, your mileage may vary, but that's the basic idea. And if you only have a single core, then of course, the threads in the fork join pool can be multiplexed on top of that. But if you only had a single core, then you're probably not going to get a big boost in performance unless it turns out that your tasks happen to be I/O bound. And then you might get a boost in performance depending on various factors having to do with the way in which memory is moved around and I/O is moved around between hardware devices and other parts of the system. The final phase in this split-apply combine phase is the combine phase. And what that does is it takes the results from the various subtasks and it joins them back together again. And so there's a join method that corresponds to the fork method, and join logically waits for a subtask to finish. Now, we'll see when we get into the details of this later that join doesn't actually block. It actually pitches in and does some processing as well. But you can think about it as logically blocking in the sense that the execution doesn't continue until the subtask that join is waiting on has completed. And we'll talk more about that when we get into the details of how fork and join work, when we get into the details of the fork join pool classes that will occur in just a little bit. The other thing that join does is it merges the results back together again. So you end up with composite results that correspond by taking the results of the different, basically the different child processes, child subtasks, and then joining them together in the parent. And that happens recursively until you have a single combined or so-called reduced result. Okay, another thing to note here is that join occurs in a single thread at each level. So when you join, what you're doing is that the parent thread is getting the results or the sub-results from the different subtasks that are running in the children threads. And as it turns out, there's no need to do synchronization here because of the very clever way in which the fork join pool operates under the hood. So you don't have to do any synchronization in your code because that's all handled for you by the framework, which is yet another reason why these modern Java frameworks like fork join pool, like the parallel streams framework, like the Java Completable Futures framework, like the reactive streams framework, such as RxJava or Project Reactor, tend to require very little, if any, synchronization in user code. There's situations where you need it, but oftentimes you can avoid it because you're not dealing with shared mutable state. And that has to do with the way in which the frameworks are designed very cleverly to handle all the details related to moving things around between the threads. So that's a quick overview of the Java fork join framework. Again, just enough to kind of give you a high-level perspective, a gestalt, as they say, and naturally we'll go into a lot more detail as we go further along.